All right, open up your book to section 4-6. We're on page 221 in your book. The title of this section is Partial Fractions and Operations with Rational Expressions. And the objective was to multiply, divide, add, and subtract rational expressions and resolve proper algebraic fractions into the sum of two or more partial fractions. And that's the part that we're going to tackle here today, is to come up with the partial fraction decomposition, is what it's referred to as. So the partial fraction decomposition, or resolving into partial fractions, those mean the same thing. It's the process of reducing a fraction into the sum of two or more simpler fractions, is the idea of partial fraction decomposition. So let me give you an example here from our rational numbers first of all. If I gave you the number 5/6, I could resolve this into a couple of simpler fractions, or the sum of a couple of simpler fractions. If I notice that 6 has factors of 3 and 2, and so therefore I can write this as 1/3 plus 1/2. Again, I got to be able to factor that denominator. If I can do that, it will help me, give me a hint as to what denominators I need. Now, as far as knowing what numerators to pick there, that does take a little bit of work to figure that out. But it turns out 1/3 plus 1/2 would end up giving me 5/6. In other words, you could do the same thing, say, with 4/6 or 3/6, but the numerators wouldn't be 1 and 1 in those cases. This extends to rational functions as well, or rational algebraic expressions. That if I have something like 7x plus 2 over x squared plus x, and I want to resolve this into its partial fractions, that is, I want to come up with two or more fractions that I could add together that are simpler. Again, the first thing you have to recognize is that that denominator factors into x times x plus 1. That's the hint I need to figure out my denominators for those two fractions. And then it would take a little bit of work again to figure out what the numerators are, but it turns out that you could write this as 2 over x plus 5 over x plus 1. If you were to take that end result and get a common denominator there, add those two together, it would turn out to be 7x plus 2 over x squared plus 1 when you get done, or x squared plus x when you get done. All right, so how exactly do we do that? Let's go through an example here. Take a look at example 3 on page 224. And we're going to use the technique here of solving this using a system of equations here to solve this one. But example number 3 on page 224 says to resolve into partial fractions this guy right here. And they've actually already factored this for us, so that was nice of them. It doesn't always end up being factored. They have 8x minus 1 over x plus 4 times x minus 7. So again, that could have been just written in a quadratic form in the denominator, and then you'd have to factor it like our example on the previous slide looked. But that was nice that they factored this for us. So if you want to use a system of equations to solve this, then it turns out that I can write this in this form here. I have already factored it, or they gave it to me factored, so I know my denominators for these two fractions are going to be x plus 4 and x minus 7. That's the first step, is I got to be able to factor the denominator. The question is, well, what numerators do I need? It's not going to be the 8 and the negative 1 that you see in the original problem there. All right, I don't know what they are. So I'm going to give them a name here, an unknown. We'll call them a and b. We got to do some work to figure out what a and b are equal to. All right, so the way to solve this is we're going to take this whole expression here, this whole equation, I should say, and we're going to multiply the whole thing by this denominator that I see over here on the left side. So we're going to multiply everything by x plus 4 times x minus 7. I'm multiplying both sides of this equation by that quantity. Basically what I'm trying to do is get rid of the fractions. All right, notice what happens on the left side when you do that. That turns out to be pretty nice because the x plus 4 and the x plus 4 in the denominator will cancel out. The x plus or x minus 7 in the denominator cancels out with that other x minus 7. So this just turns out to be 8x minus 1. That's really nice. Notice what happens here with this first fraction. When I multiply x plus 4 times x minus 7 times this first fraction here, look what happens to the x plus 4s. They will cancel each other out. I'll be left with a times x minus 7. And then do the same thing now, distribute to the last fraction there, b times, or b over the x minus 7. When I multiply by this x plus 4 times x minus 7, this time the x minus 7s cancel each other out, and I'll be left with b times x plus 4. Again, our goal in that first step was to get rid of the fractions, and that's what we've done. Okay? And now let's rewrite what we have over there on the right side. I'm going to leave the left side alone here for the moment. And let's distribute the a through the parentheses as well as the b through those parentheses. So I'll have an ax minus 7a, and I'll have a bx plus 4b. And now let's combine like terms at this point. We're looking at the x's, and I guess there's two terms that have an x in it, and there's two terms that don't have an x in it. So these two terms right here, ax and bx, those both have x's in them. So again, the left side I'm going to keep as is. And let's write this as ax plus bx. I'll put those in parentheses just so I can see that I'm associating those two together. The other two terms that I have here don't have x's in them, so we'll just combine those two together there. So that's plus a negative 7a plus 4b. That's what we have there. And I'm going to rewrite the first part of this one last time here. So I've got 8x minus 1 on the left side. Since each of these terms here in the first associated pair here have an x in it, let's factor out that x. In fact, I'll factor it out and put it at the end here and write this as a plus b. That quantity is multiplied by x. And then plus negative 7a plus 4b. Now, if you look at closely what we've got here, over on the left side of this equation, I've got 8x minus 1. That right there would be classified as a linear expression. It's in the form of mx plus b. If you look closely at what I've got over here on the right side, I've got some number times x plus some other number. That's in the form of also mx plus b. This would also be linear in form. I've got two linear expressions that I'm setting equal to each other. Now, the only way these two linear expressions can be equal to each other is if their individual terms are equal to each other. Probably the best way to think about that is think about this graphically. If you have one linear function sketched and I have another linear function sketched, what's the only way possible for those two functions to be equal to each other? They have to have the same slope. That is, this 8 right here has to be equal to this a plus b. And they have to have the same y-intercept. That is, this negative 1 would have to be equal to this negative 7a plus 4b. In order for these two linear functions to be equal to each other, I have to have the same slope and the same y-intercept. Now, it turns out that this same concept we're talking about here with linear functions would extend to any polynomial. It doesn't matter whether it's quadratic, cubic, and so forth. That same thing has to be true. So what I can do now is I can rewrite this as two separate equations. I can take the 8 on the left side and set it equal to the a plus b from the right side. And I can take the negative 1 on the left side, my y-intercept, and set it equal to the negative 7a plus 4b that I have on the right side. Now what I have here is a system of equations that I want to solve. And you've got several ways that you can solve a system of equations. In fact, we just dealt with this in the last chapter of being able to solve a system like this. I think I'm just going to use the elimination method to do it, but you could certainly use substitution. You could even grab your calculator and do some stuff with matrices. There's lots of ways you could do it. But I think what I'm going to do is take this first equation though, and I'm going to eliminate the a just because that looks like the easiest thing to eliminate here. I'm going to take that first equation and I'm going to multiply it by 7. And when I multiply by 7, what do I end up with? When I multiply by 7, 7 times 8 is 56 is equal to 7a plus 7b. And the second equation, I'm not going to change him at all. So that's a negative 1 is equal to a negative 7a plus 4b. And again, the only reason I chose this way is because the 7a in the second equation was already negative, so I could just multiply by a positive 7 in the first equation to eliminate that value. But you could choose to eliminate the a or the b, and you can multiply either equation by whatever quantity you wanted to do that. So what do we end up with? 56 minus 1 is going to give us 55. 7a minus 7a, those cancel each other out, and that's equal to 11b. 7 plus 4 is 11b. And so dividing by 11, it looks like b is equal to 5. B is equal to 5. And now that you have that, you can take either one of these equations that we started off with and go back and substitute in that value of b. I'll just take that first equation there. So if I have 8 is equal to a plus b, and I know b is equal to 5, that means that 8 minus the b is equal to a. And again, b is equal to 5, so I have 8 minus 5 is equal to a, so a must be 3. Those are the numerators that I need. A is 3 and b is 5. That's these guys right here that I was looking for. Okay? So let's rewrite this down below. So I've got 8x, oops, let me do that in black, it's fine. We've got the 8x minus 1, and we're dividing that by x plus 4 times x minus 7 was the equation they gave us. Let me make sure I wrote that down correctly. X plus 4 minus, or x plus 4 times x minus 7. And that's equal to, again, it was a divided by x plus 4. So that's going to be 3 over x plus 4 plus b, which we found out was 5, over x minus 7. And that right there is our partial fraction decomposition. We've now rewritten this in the form of the sum of two simpler fractions. This technique works regardless of how many factors you have in the denominator. If it turns out that it's like this one where it's quadratic, that's fine. If it's cubic, quartic, whatever, as long as you can factor that denominator and write it as the sum of that many fractions. So if it's cubic, you'd have a third fraction you add on. If it's quartic, you'd have a fourth fraction you're adding on, and so forth. And obviously, this system of equations gets more and more complex. And in those cases, you'd probably want to definitely grab your calculator and use matrices to solve that. Let's talk about another way that we can solve this, though. There's a technique called the Heavyside Method that we can use to actually to solve this if we're working with linear factors in the denominator. If they're nonlinear factors, if they don't reduce any further than, or if they're repeated, then you got a few more steps you got to use, or you got to use that algebraic technique that we just saw. Heavyside method here, though, is named after a guy named Heavyside, thus the name of it. But here's the method that he came up with for doing this same task. If you can factor the denominator into n linear factors of the form x minus k sub I, which we already had in our previous example there, we had x plus 4 and an x minus 7. Linear factors. And then if you can write as the sum of n fractions whose denominators are the linear factors, x minus k sub I, which again we did that. We were able to write this as some number over x minus plus 4 over some number plus some number over x minus 7. But then the faster way to find those numerators here's what you can do. You can cover up one factor in the denominator of your original fraction. So you'll cover up, for example, the x plus 4. And then you'll do a substitution into what's left from what you forgetting about what you've covered up, leaving that out of there, but from what's left, substitute in the x value. That would be the k sub I, or in our case, if it's x plus 4, it would be a negative 4 that we're going to substitute in. Substitute in the x value that makes the covered up factor equal to 0. So again, if you're covering up x plus 4, then x equals negative 4 would make that equal to 0. And then it turns out that the result that you get when you do that, the result is the numerator of the fraction with the denominator of x minus k sub I. So that gives us one numerator, and then obviously you just have to repeat this process to find all of the numerators that you need. Now, in the previous example, we only had a quadratic in the denominator, so I only had to do that twice. But again, you might have to do this 3 or 4 times, depending on the degree of that denominator. All right, so let's try using this method. Let's go back and solve example number 3 again. But this time, we're going to use the Heavyside method here. So let's write down the original problem again. They gave us 8x minus 1, and that was divided by x minus, or actually, they gave us x plus 4 times x minus 7 is the way that they wrote that for us. They already wrote it in factored form. That was nice of them for us to do it that way, but they didn't have to. They certainly could have done that without factoring that for us. All right, so I can rewrite this then, I know, as some number over x plus 4 plus some number over x minus 7. Again, we've already gone through the work and figured out what the number should be here, but let's see how the Heavyside method will speed this up for us. All right. So what I want to do is I want to cover up one of these factors here. I'm going to start with the x plus 4. I'm going to kind of write down my steps here that I'm going to do here. So I'm covering up the x plus 4 on the left. Okay, so when I do that, I'm left with just 8x minus 1 over x minus 7. Okay, I've covered up the x plus 4 that you see in the denominator, so that's what I'm left with. All right, the second step is you're going to plug in a value of x that would make that factor that you're covering up equal to 0. So we're going to plug in x equal to negative 4, and everything that remains there in that equation, everywhere that I see an x, I'm going to plug in x equals negative 4. So what does that mean? I'm going to have 8 times, instead of x, it's going to be a negative 4 minus 1 in the numerator. And then I've got a negative 4 instead of an x in the denominator, minus 7. Now what's that turn out to be? If I evaluate that, I've got a negative 32 minus 1 will be a negative 33 in the numerator. And then a negative 4 minus 7, that's a negative 11 in the denominator. And negative 33 over negative 11 sounds like 3. That right there is the numerator for the factor that I was covering up. That turns out to be the numerator right here. That's that 3. That's the third step. So that means that 3 use 3 over x plus 4 on the right. All right. That's the process that we've gone through. We're going to do that again now because I now figured out what the numerator is for the first one, but now let's do the second one. So let me do this in another color here. I'll start these steps over again. So the first step is we're going to cover up the x minus 7 on the left. That is on the left side of our equation. So we'll be left with 8x minus 1 over x plus 4 is what remains if I cover up or eliminate the x minus 7. The second step is you're going to plug in a value. You're going to plug in a value for whatever made that x minus 7 equal to 0. That would be x equals 7 then. Plug in x equals 7. And what are we left with if we do that? We'll be left with 8 times 7 minus 1 in the numerator, and then 7 plus 4 in the denominator. So what does that simplify to? 56 minus 1 is 55. 7 and 4 is 11, and that becomes 5. And check that out. That right there is the numerator for the x minus 7 term. I'll write that down. So then use 5 over x minus 7 on the right. Okay. Definitely that's a lot faster. Obviously I'm writing down all the steps that I just went through, but you certainly can go through that pretty quickly then to figure out what those numerators need to be. That right there is partial fraction decomposition, or resolving into partial fractions. And this is using the Heavyside method. That's the end of the second half of section 4.6.